So now we get back to the main thrust of the video, which is why should I care about standard ML? Well, first of all, should you care about standard ML? Well, uh, if you're not a programmer, you shouldn't. If you are a programmer, I really wouldn't say uh, about caring about standard ML specifically. Just caring about the sort of the ideas behind functional languages. But as for standard ML, I think that those people that I talked about who decided to give up on coding in it, a lot of the reason, the reasoning why for a lot of those people, I would hazard a guess and say was because standard ML has a lot of daunting features, but they are nice features for a language to have. And the first one is, or at least the first one I'm going to talk about, is this document here called the definition of standard ML. So it does seem daunting to have a over 100-page document that describes the language because, well, do you have to read it? Well, to get started, I really don't think you do. If you're going to dedicate your life to programming in this language, you probably should. But what's really nice about this is that it has a definition. If you're at all familiar with C or C++, you are familiar with the concept of undefined behavior, which is behavior that, you know, that, well, is undefined. But what it means is that if you have certain snippets of code in your program, if your program is coded a certain way, what it will do depends on either the implementation of the language, which basically means the compiler you're using, or it will depend on the uh, the contents of memory that's sort of outside of the bounds of what you want to look at. So if you feed a string into a C function, into like a C library function, and that string does not have a null terminator because strings in C are encoded by having after the very last character a null character. What might happen is that your the library function will keep on reading until it finds a byte that's 0 that is equal to the null character. Or you'll get a segmentation fault because it will go outside the program's memory space and it'll crash, which I'll get to later. Why I think that's probably the better occurrence because at least you'll know there's a bug. So, standard ML has this very precise mathematical definition. If I go to some random page, you see a lot of mathematical stuff. So the idea is that the language is very specifically defined to help with platform independence, to help with the idea that you should know the behavior of, have a very good idea of the behavior of what you're coding before running it. So you don't have to reduce testing, and standard ML does a lot of things that will reduce your need to debug, which are nice but daunting features. And I'll get to them in a bit, but the language is, it's a functional language, as you've probably guessed by now. And it's an impure functional language because you can define what are called reference cells, which are objects that keep their state, and you can modify them in one part of the code, and when you access them in another part of the code, they'll be different. So, and what it doesn't have is any sort of for loop, while loop, for each loop. No go-tos, which is just great in general, but it relies solely on recursion, and after or while going through some examples of C code versus standard ML code, I guess, explain at a very high level why the recursion isn't actually a bad thing. So, quick disclaimer here. I'm going to be comparing standard ML to C a lot. In fact, I already have. And I've already done a disclaimer. The idea isn't to crap on C. I'm going to be using a Unix command line here. I can't exactly complain about the language, like complain too much about the language that was literally designed in order to create Unix. However, as I said, it's a very good contrast because, well, I'll get right to that. So we have a little C program here. It takes in the square, it takes a square of an integer. So we take an integer, -5, we square it, and then we print it out. We take a float, which is -5, we square it, and we print it out. We take a float, which is 1 billion, square it, and print it out. So what happens when we compile it? Well, it compiles. What happens when we run it? Well, the square of our int is what it should be. Square of our float is what it should be, but the square of our second float is a negative number. So, you know, even if you can't figure out what the square of a billion is off the top of your head, you probably know well enough to know that it's greater than 0. So, what's going on here? Well, what's going on here is that there's a lot of implicit typecasting going on. This float here is being cast into an int, and that's fine because it's -5 exactly. So there's a match up there, but this here is 1 billion, and we're getting this, and this 1 billion squared is definitely, what is it, a quadrillion? It doesn't really matter. What matters is that this, goes here, tries to. Uh, I can't think off the top of my head of what the maximum value of an int is, but it's less than 1 quadrillion. So it tries to. This here, this a times a, cannot fit into that integer. If a is a billion, cannot fit into 32 bits, so you get nonsense out. So, moving on, this is a sort of an equivalent-ish program in standard ML. It doesn't have the whole 1 billion thing, because, well, we don't need to. Really, that's not the point. What the point is that if I try and compile this standard ML code, uh, we get error. Operator and operand don't agree. The operator domain was int and the operand was real in the expression square of -5.0. So standard ML has very strong type checking if the types of two variable, like if you try and feed a real into a function that has an input type of int, you'll get a compilation error. And in standard ML, you do get a lot of compilation errors, and this is a nice but daunting feature because if you code up if you make some coding, you get compilation errors, that sucks. But here's the thing. What sucks even more is getting silent errors, like in the C code, or, or crashing, having a runtime crash. So this, you know, this whole typecasting is dangerous thing isn't just a theory thing. There was this pretty infamous case of typecasting where the first flight of the Ariane 5 rocket used flight software which at some point cast a 64-bit floating point number to a 16-bit integer. So in C parlance, that's a double to a short. And what happened is that overflowed and the flight software crashed and the rocket did not make it to orbit. And putting on my armchair rocket scientist hat for a bit, it is a very well designed rocket and has been very successful in spite of this fact, but the fact remains that because of unsafe type checking, it became one of the most expensive bugs in history. So the moral of the story is this, type checking is unsafe, and standard ML recognizes that by not really allowing implicit typecasts.